In this video, I'm going to take you through representation of a phasor as a complex number. In our previous lessons, we learned that a phasor is used to represent the direction of an AC circuit, current, or a voltage. And you realize that in an AC circuit, current and voltage are not in the same phase. So you have I and you have V. In an AC circuit, the current and the voltage are always out of phase and they are separated by a phase difference, which is a phase angle. So you can have your V and your I separated at this way. Sorry, this phi. So that is how the voltage and the current in an AC circuit behaves. For that reason, we can apply the concept of complex numbers here to make simplification of parameters concerning AC circuits easier. So let's see. In our previous lessons on RC circuits or RL circuits, so in the RL circuits, you realize that the current was in the same phase with the voltage across the resistor, right? So our VR was here and our VL was here, and we had the voltage pointing here with a phase angle of phi here. And you know that to find the component I down here is simply what? Our voltage here cos theta, or the parameter here cos theta. To find what you have here is the V or sin theta. So I cos what? I is equal to V cos phi, then our V here, our VL here is equal to this V sin what? Phi. And when you have these things, you can easily represent them as complex number. When I say a complex number, what do I mean? From algebra, you realize that a complex number is any number which has a real part and an imaginary part. So the real part of a complex number is represented as what? A. Then the imaginary part is represented as B. Then we have an imaginary operator which we say is I, but in the context as we are going to apply it in circuits, it's advisable to represent it with what? J, to avoid confusion with current I. So A plus BJ. Once you have this notation, we say this is a complex number. It has a real part A and it has a complex part B, right? And our operator is attached to the complex part always. Now, our complex operator J is just equal to square root of negative 1. So the square root of negative 1 has been accepted represented by this operator J. And we can also draw complex number graphically. So a complex number can be represented as, I have a complex number I here, and I have the x-axis, I have my y-axis. There will be a theta here, right? So you know that my complex number will have a real part ix, which is equal to what? I cos theta. Then it will have an imaginary part which will have iy, so I sin what? Theta. So this is how complex numbers are represented. The imaginary part is always on the y-axis and the real part is always on the x-axis. Real part is equal to I cos theta and imaginary part I sin theta, right? So we have some things you have to know about complex numbers, and you know that you have the length of a complex number I will be equal to the square root of our ix squared plus our iy squared, and this is what we call the modulus of a complex number. So in AC notation, you realize that this becomes the magnitude of either the current or what? Voltage. The magnitude of current or voltage. Then we can also have the angle theta to be equal to tan inverse of what? Iy over ix and this will also represent our phase angle. So we want to employ the concept of complex number in AC circuits. So these are some of the properties of complex number which we can apply. So complex number operator J in AC circuit will be equal to the square root of -1. Right. Then also you have j times j to be equal to -1. Since j is equal to square root of -1, then j times j is simply -1. Then whenever you have 1 over j, this is equal to -j. Why? Because 1 over j, you rationalize and you'll give me j. J times j is -1, giving me this I have here. Right. So these are some of the properties of a complex number. So the operator J can also be applied with rotation about our axis. So the operator J, when applied to a phasor, turns the phasor through 90 degrees in the anticlockwise direction without alternate length. So when you apply this operator J, it turns the phasor through 90 degrees anticlockwise without alternate length. So these are some of the properties of the operator J which you want to employ in AC circuits. Then what are some useful algebra formulas which you need? You realize that when you have R1 theta over R2 theta, so let's say theta 1, theta 2, this is the same as R1 over R2, then theta 1 minus theta 2, right? So this is the angle. This These are algebra rules we're using our complex number notation in our electricity. We also have our x plus jy. Then this is what we call the conjugate. It's going to give us x minus jy, right? Then you also have r theta. If we take the complement, it's also giving r, the negative, the angle. So when you take the complement, the magnitude is not affected, but the angle is rather what turned, right? So these are the basic useful algebra we use in AC circuits. Thank you for being with me in this video, and I'm going to show you how to solve and apply this using complex number. Okay, so let's take some examples to solve. So at this point, see, using complex numbers to solve AC circuits. Let me take you through that part. So thank you for watching this video. Please don't forget to subscribe, like and share.